In this screencast I'm going to look at finding the Taylor series of two functions of z, where z is a complex variable. And for the first one, the function I've chosen is the log of cosh of z, and I'm wanting to find the Taylor series of this function about z equals 0 up to and including the term in z to the 6. After that, I'm going to be finding the Taylor series of f of z equals tanh z, but we'll leave that one for now and come back to it later. Before we start, let me just remind you what capital L log z is. It's defined to be ln of the modulus of z plus I times the argument of z, and it's called the principal logarithm of z. And it's in fact defined for z complex except at z equals 0. But you should notice that the log of cosh of z, which is what I'm asked for here, that's perfectly well defined at z equals 0 because cosh of 0 is 1. So what I'm wanting to do is find the Taylor series of f of z, that one with the arrow there, the log of cosh of z. And in order to do this, I'm going to use some standard results, which I shall write out here for you. You should make sure that you do know how to derive these, but usually they are given and you can just refer to them if you need them. So this one is valid for all complex z. That's the Taylor series for cosh of z about z equals 0. And we've also got a formula for the log of 1 plus z, and that one is valid for the modulus of z less than 1. But in fact, as you can see, what I need in this case is the log of cosh of z. So what I'm going to do here is just let w equal 1 plus z, so that in fact z is w minus 1. And what I in fact have there then is that the log of w is w minus 1 minus w minus 1 squared over 2 plus w minus 1 cubed over 3, etc. And that one is valid for the modulus of w minus 1 is less than 1. So it's these two results that I'm going to be using to obtain my required Taylor series. That one that's boxed there and this one that's boxed here. And what I'm going to be doing is using what's called the composition rule, and I'll show you what I mean. What we're asked for is the Taylor series of the log of cosh of z. And what that is basically I take my boxed result here, and what I'm going to be replacing w by here, that is cosh of z. So each of my bracketed terms on the right hand side is cosh of z minus 1. And you can see from this box up here what cosh of z minus 1 is. It's going to be z squared over 2 factorial plus z to the 4 over 4 factorial, etc. So I've got to scroll down to do this, but basically putting this function, substituting one into the other, this is the w minus 1 term. So that's this first term here. Then I've got w minus 1 all squared. And then I've got, and that's multiplied by a half, and then I've got a third of w minus 1 all cubed. And I hope you can see that in each case here I'm retaining just the values that I need, and I am not taking, for example, a z to the 6 term here, because by the time I've squared that bracket out, that's not going to be important if I'm only looking up to and including the terms in z to the 6 overall. So make sure you don't discount terms that are needed, but equally well do discount ones that are not needed. It will make the algebra easier. All you now have to do is simplify this expression and just retain the powers up to and including z to the 6. So I suggest you stop the screencast now for a moment and try to do that, and then restart it when you're ready. And what I'll now do is write down what the answer is for this. It is z squared over 2 minus z to the 4 over 12 plus z to the 6 over 45, and the other terms which are not important in this case. And the composition rule says that there is an r greater than 0 for this series to hold for all modulus of z less than r. We don't know what little r is in this case, but we know that it does exist and it is greater than 0. So that is the required Taylor series for the first function that we were given. If we now look at what the second function was, the second function was f of z equals tanh of z. And what I'm going to do here is use the differentiation rule, which basically just allows me to differentiate both sides of a Taylor series in order to obtain another one. There's slightly more to it than that, but that in an informal way is what we're doing. And if we go back up for a moment, I hope you can see that if I differentiate this term, I do get cosh in the denominator and shine in the numerator, so I do indeed get tanh of z. So all I need do is, if I differentiate the left hand side, I also have to differentiate this right hand side, and then I'm done. So what we have is the Taylor series for tanh of z is the derivative of this right hand side, so it's 2z over 2 minus 4z cubed over 12 plus 6z to the 5 over 45, and that is z minus z cubed over 3 plus 2z to the 5 over 15. And that is valid for mod z less than r. And in this case we are in a position to state a suitable value of r, because we know that tanh of z is analytic on this set here, z such that the magnitude, the magnitude or the modulus of z is less than pi by 2. So what I can do is take little r to be pi by 2 here, and then the series that we found is valid for the modulus of z less than pi by 2.